Okay, so heat transfer in the atmosphere. This lesson reviews radiation, conducting, convection for the 5th time, but it gets into the budget of the Earth, the Earth's heat budget, and we're going to have some good systems terms, some good input-output internal processes going on, and we just got to get going on this. So radiation. Now radiation is something you're very familiar with, whether you know it or not. Okay? Right now, you're using radiation to look at me. What do I mean by that? Light. What you call light is radiation. And instead of wasting time, let's just get to it. It's energy traveling through electromagnetic waves. That's the radiation I'm talking about. And what do you think? Are the big waves going to be the ones with the highest energy, or the little waves that are tiny? You remember that. Okay, and the way you remember that is make a big slow wave. And then try to make a tiny one. Faster. Faster. It's really hard to make that tiny, tiny, tiny wave. Okay? So the shorter the wavelength, the higher the frequency, the higher the energy. So the smaller the wave, so these little tiny waves here, we end up with very, very high energy, whereas these large waves have much, much lower energy. So, start at the top or the bottom? Start at the top. What wavelength, or what type of electromagnetic wave has the most energy? What do you think? The same one that made the Hulk. Gamma rays, all right? So gamma rays are the smallest. On 1 millimeter, you can fit billions of gamma rays. They are that small. They are that tiny, that everything else. Moving down the list, though, what's next? Go to the doctor's office. They need to look in your bones. Give you an X-ray. Okay, now here's another one. We're going to skip it for a second because I want to talk about the little rainbow we have on the screen. What are those? Thank you for remembering that. Now, visible light is actually a really small part of the spectrum. What we see is all the colors that we've seen through our whole life is a really narrow section of that electromagnetic spectrum. But we have the colors red, yellow, green, blue, violet, or purple, and those are in order. So if we try to get back to the one I skipped here, and violet's the one closest to it, what do you think is in between visible light and X-ray, Ian? UV stands for what? Ultraviolet. Ultra. So there's ultraviolet light, and that's right here, just a little bit more energetic than what we can see. And there are some little crustaceans like shrimps that can actually see ultraviolet light. Butterflies can see it too. So they're seeing colors we can't even imagine. It's very cool. On the other side, if we go down the spectrum, the last color, the least energetic color, is red. What do you think's on this side of red? What is it? Infrared. And infra, we looked it up an hour ago, means below or under. So infra. Now, here's a fun fact. You're all in a room. That room is about 70-some degrees. You're giving off infrared light into this room. You're radiating that heat away. And if I had an infrared camera, that camera would be the brightest where your faces are. Your eyes would be the very brightest, your noses would be bright, your mouth and your ears would be the bright parts of your face. Your clothes would be darker, the tables, the floor, everything else would be much darker than your face. You're radiating that heat away, so why aren't you feeling cold? Why?
Because you're giving off the heat.
You're giving off the heat, but what's the room giving back to you? Yeah, this room is radiating 70 degrees worth of radiant heat. You're getting it from the floor, you're getting it from the walls, you're getting it from the ceiling, you're getting it from the table. The person next to you is radiating heat away. You're getting some of that heat. All right, I had two girls last class. They put their cheeks really close together, and their cheeks felt warm. If you just put your hands like this, your hand will feel a little bit warmer right away. This hand is radiating heat into that one. This hand's just like if you put your hand close to a mirror or a tinfoil blanket or a mylar blanket or some tinfoil. That heat that you're losing comes right back at you. So that infrared heat, it's kind of a big deal, and we're going to get back to it. Lastly, last two, beside infrared heat, you've probably used these today. Microwaves. You use a microwave to microwave your food. Yeah. Microwave. And you know the little screens in the microwave doors that you can look through?
Yeah.
Those little holes are too small for a microwave to fit through. They're basically like little mirrors for the microwave. So the microwaves hit that screen and it bounces off. That's why you can look at it without your face getting warm. If you took that screen off and just looked through the plastic, your face would feel hot just looking in a microwave. So definitely don't do that. It would be dangerous, but anyway, the largest one is a radio wave. You've had radio waves going through your body your whole life. They're going through this room right now. If I had a little radio, I could turn it on, use a little diode, and I could tune that radio to a certain frequency. All right, so that's radiation. Conduction. Conduction should be reviewed as well. But conduction is where you have heat molecules that are traveling by doing what with each other? You got the fast ones and you get slow ones right next to it. What's happening?
Bounce each other.
Pretty much that's it. When heat travels by molecules bouncing into each other. And we're not going to belabor this one because conduction of heat, it's really not that complicated. You've got molecules that are moving really fast, back and forth. On this end you have molecules that are just barely moving at all. And as these molecules bounce into each other, that heat makes that heat travel from the hot to the cold. That's conduction. The last one we'll talk about is convection. And for this we have a little demonstration. All right, so here's our little demonstration. On this side I have some ice. Over on this side we have light bulbs that are heating the air up. So we have cold, we have hot. And what I'm going to add here is some canned smoke. And so as I add the smoke, it's a lot of smoke, but what you end up with is you're able to see how the air on this side it's more turbulent, it's rising up. This guy's in the way a little bit. But hopefully you're able to see how this is where it's rising. The air should be coming through and up. Okay. Why is this air the more dense air, the air that's sinking?
Cooler. Because
Yeah,
it's
it's
more dense.
It's cooler, it's more dense. What's happening as it comes over here? It's heating up and it is rising. So one more time. No, this is not a perfect demonstration. But we end up with this air kind of swirling in this side, trying to force its way up over here. This end ends up being clear. Like right now there's really nothing over here because all of the air is filling into here. I put my hand in the bottom and it feels, I can feel a thin layer of cold air right at the very bottom. That most dense icy air is. And over here you have more and more heat rising up. So convection is the movement of warm material upward and cool material downward. sure you add in your notes that the hot air rising is less dense, and the cool air sinking is more dense. Okay, onward to the last point, Earth's heat budget. This is the point of what we've been doing here, Earth's heat budget. So we have basically a blank Earth here. What are the inputs to this system? So an input, okay, if I gave you $10 and you spent $10, what would be happening to your money supply?
You gain a toy.
Okay, you wouldn't be saving any money though, right? If I gave you $10 and you spent $10, okay, that's a net zero. If I gave you $10, you spent $8, what would happen over time?
You have 2.
You'd have $2 and $4 and $6. If I gave you $10 and you spent $12, you minus 2, minus 4, minus 8, minus everything else. That's what kind of a budget we're talking about here. But instead of being money, it's going to be heat. The Earth is gaining heat from a source. Take a wild guess.
Sun.
All right, the input is radiation from the sun. From the sun. Okay? So radiation from the sun. The output. The output, you'd have a hard time guessing this, but that's radiant heat from the Earth. So radiation from the Earth into space. So just like we are radiating heat away from our bodies, the Earth is radiating heat up into space. And it's a budget. So we have radiation coming from the sun, and we have radiation leaving the Earth, and it needs to be at least balanced. Just like you need to, not spend more than you earn. If I give you $10, spend $10. If I give you $10 and you only spend 8 of them, you still got $2 somewhere. Okay? Well, for our final drawing, our input side is the sun. Okay? What's on our output side? Yeah, so that radiant heat coming from the Earth. Now in the middle, there's another thing we need to talk about, briefly. All the other stuff that we've talked about so far ends up in this middle category. If I give you $10 and you go to the bank and get 10 ones, have you really done anything?
No.
But you've done something, right? There has to be a word for this. The word is a internal process. So an internal process is something that happens within the system that doesn't affect the inputs nor the outputs. So the internal processes in our case here are any convection and any conduction. I give you $10, you go to the bank, get 2 5s. That's an internal process. You haven't spent any, you're not getting any more. The output would be spending it, the input would be how much you get.